Subnetting basics. Subnetting is like skydiving. You must understand the tools and the processes involved before you jump into it. All right, no pun intended. In this nugget, we're going to prepare you for your subnetting adventure by starting out looking at the decimal to binary conversion technique. Then we will finish the IP classes discussion from the last nugget. We will also look at the hierarchical addressing set up by IP. This hierarchy will result into an IP address being divided into what's known as its natural parts. We're going to identify them here. And then we're going to end up with a look at the tool that makes subnetting possible, and that is the logical AND. The first step in subnetting is to understand the decimal to binary conversion technique. So let's start out here. I'm going to give you a fact. This numeric value and this numeric value have the same value. All right, now let me explain why. This is a decimal number, so we'll be dealing with decimal up here, and this is a binary number. Now, each of these number systems have their own base. With the decimal number system, you have a base of 10, and with the binary number system, you have a base of 2. What does that really mean to us? When we're setting up place values, which is starting from the right, moving to the left, the first place value that we have here is going to be the base, which is 10 in this instance with decimal, to the 0 power. Once that happens, that's going to equal 1. So our first value is 1. Then you just keep incrementing up. 10 to the 1, that's 10. 10 to the 2, that's 100. And then you just keep going up. 10 to the 3 is 1,000. This is how you move in place value in a decimal number system. In fact, in any number system. So we have the value of 1, 10, 100, and 1,000 as you see them here. Now with the binary number system, the base is 2, but you do the same thing. 2 to the 0 equals 1. So the number system is going to start with 1, just as the decimal system did. Then we're going to go 2 to the 1, which equals 2, 2 to the 2, which equals 4, 2 to the 3, which equals 8, and you continue down the line. Now these number systems can progress as far as you want them to, right? I mean, that's why we have infinity, because people got tired of trying to count to the end or finding an end to these systems. So in this instance, we have two number systems. Both of them have bases. The bases are different, 10 and 2, and those bases decide the place values that we see here. So let me give you an understanding of what we're dealing with. When I say 172 in a decimal number system, what I'm saying is this place value is a 1, this place value is a 7, and this one is a 2. Let's look at the results of that. 2 times 1 is 2. 7 times 10, which is the place value here, is 70. 1 times 100 is 100. Now all you do is simply add these up, and you come up with 172. So this is the breakdown of how decimal works. So now let's figure out how binary works. If I have a number, as I see here, with these values, 0, 0, 1, 1, 0, 1, 0, 1, and I want to prove that their value, or the value of this number, is the equivalent of decimal 172, I'm going to go through a similar process that I did up here. I'm going to say 0 times 1 equals 0. 0 times 2 equals 0. 1 times 4 equals 4. Finally, I have a value here. 1 times 8 equals 8. Then I have a 0 in the 16th place, so that's a 0. A 1 in the 32 place, turns it on, so that's 32. A 0 in the 64 place, that makes it 0. And then 1 in the 128th place. So what I'm going to wind up with is adding these values together, I'm going to come up with a decimal 172. And this is the way we prove that 10101100 in binary is the equivalent to 172 in decimal. Pretty cool, isn't it? And at the same time, pretty easy once you understand these place values. 1, 2, 4, 8, 16, 32, 64, 128. It's really not a problem. And in fact, I want to point out something to you here. If you will note, in our decimal number system, each place here has a range that can be associated with it, between 0 and 9, any value in there. And that's why you see a 1, a 7, and a 2 here, any number between them. When I'm talking about binary, the range is a lot smaller. I have 0. This isn't between, this is 0 or 1, okay? So I have two states here. And that's why I can represent the same value in decimal with 3 numbers that I have to use 8 numbers to set up in a binary number system. Remember that in dotted decimal notation, our IP address is shown as 4 decimal numbers divided by 3 periods, and those 4 numbers have a range between 0 and 255. Well, it just so happens that the binary digits that I assigned here that I have in our example, there are 8 of them, and if you add all of them up together, what you're going to come up with is 255. And if you turn all of them off, in other words, there's 2 states. If you make these all zeros, the bottom end of that range is 0. So hey, there you go. It's not by chance that the decimal range here is 0 to 255. It's by design. And that's why they call each of these sections, as we stated in the last nugget, an octet, because it has 8 binary values that are associated with each of those sections. All right, so let's break down this IP address. 172 we just did. We turn on 128. 164 is off, 32 is on. At that point, we have 160, because that's 128 plus 32. So we don't want 16 more, because we're just trying to make 172. So you turn on the 8 and the 4. That's 12 plus our 160 is 172. At that point, we've got our equivalent that we wanted, so we zero out the rest. So that's 172. Now, the last 3 are going to be pretty easy, because 16 is all we need to turn on, right? So I have a 1 here, and then I have zeros in the rest of the field, and that's the binary representation of 16. Same thing holds true for 1. The 1's value here, I turn on, I turn all the rest off, and I'm going to have a value of 1, or equivalent binary number of decimal 1. Now I need a value of 2, a decimal value of 2. I put zeros in all the others, and I have a 2. So our representation, as far as binary, for this same dotted decimal notation is going to be 10101100, as we found here. Just turn the 16 on, so you have 00010000, and then here you have 7 zeros with a 1, that's the 1. You have 6 zeros with a 1 turned on in the 2's place value, and then a 0, and we have equivalent numbers. More than just having equivalent numbers, what I've done now is I've completed my decimal to binary conversion for an entire IP address. This is key in knowing how to subnet. This is the basics. This is the building block. And really what's going to help you out the most is just memorizing these place values, 1, 2, 4, 8, 16, 32, 64, and 128 in the binary world. All right, so now that we understand the conversion, I have to go back one step, and we're going to have to talk about IP classes. When we left that in the last nugget, I said that these ranges that I gave you in decimal are something you're just going to have to trust me on for now. And then later I would explain it. Well, later is now. When I say that we want 1 through 127 to be the range for a Class A address, then I have to provide you the logic behind these numbers. So let me do this. I'm going to bring up my chart for binary again. And before we get into that, I'm going to give you a rule. There's a rule that a network number cannot be all zeros. It cannot be the decimal equivalent of 0, which is all zeros in each of these binary placeholders. The reason for that is that that is considered the network number. So that's why the list here starts at 1 and goes to 127. Now that we understand that, the rule in this octet is that the first bit, or the high order bit, has to be a 0. Let me explain the bit order here. On the left-hand side here, I have the high order bit. On the far right, I have the low order bit. And all these bits flow in between. So it's saying that this first bit, which is this one here, has to be a 0. Other than that, it doesn't care what happens with the rest of the bits. So let's demonstrate that. If I have a 0 here, and then I have zeros throughout all of these other placeholders except the last one, because remember, I can't have 0 as a network number, then my first possible value here is equivalent to the decimal 1, all right, because we have the 1 is the only one turned on. If I had all zeros, except for this value here, now I have the decimal equivalent of 2, still a Class A address, all the way up to the point that I had a 0 in the first bit, the high order bit. All the rest of these are 1s. If that happens, I add up 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, and I come up with 127, which is the high end of this range. Starting to make sense now, right? The same thing holds true for the Class B. It just has a different rule. The rule here is that the first bit, the high order bit, will be a 1, and the bit to the right of that will be a 0. So I have to have a combination of a 1 and a 0 here. And the result of that is, if the rest of these are zeros, I have a value of 128, because this is the only place that's turned on. That's the low end of the range. If the rest of these are 1s here, then I'm going to have a value of 191. Let me explain that. I have 1 plus 2, which is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31, plus 32 is 63. If you add that to 128, you come up with 191, which is the high end of this range. And then the last one that we have as far as assigning host addresses out to the public is the Class C address range. And the rule there is that you're going to have a 1 in the high order bit, just as you did up here. The next bit will be a 1, and the third bit will be a 0. So the rule is 1, 1, 0. These are have-tos. Once you do that, if the rest of this is 0, what you're going to come up with is 128 plus 64. These two bits here, and you come up with a 192. Hey, it's the low order, right? The low end of the range. And if you turn all of the rest of these on, then you're going to have 1 plus 2, plus 4 is 7, plus 8 is 15, plus 16 is 31. So you have 31 plus what you had is these two combined, 192, and you come up with 223, the high end of the range. And there you have it, IP class ranges demystified. All right, now we're going to move into a discussion on the hierarchy of addresses within our system. And to do that, we're going to look first at the U.S. Postal Service. Just as we did before, this is going to be our standing analogy when we're talking about IP addressing. They just mirror each other so well. All right, I have an envelope here that needs to be delivered from house number 1 over to house number 2. Now what has to happen here, because they're in different states, is that we have to have one address here and one address here. This is the source, this is the destination. When you do that and you deliver your mail to the post office here, the first portion of the network, the U.S. Postal Service network, what it's going to do is it is going to look at one portion of the address in particular, and that is the city and the zip code. It really doesn't care at this point what is contained here, the street address. It doesn't at all. And it doesn't need to verify that that street address actually exists within this city and zip code. What it's going to do is take this piece of information and route it through its network. It can go from the post office to an airplane at the airport. Obviously, the airplane goes through the sky, lands at another airport. At that point, it goes to a local post office, and then that local post carrier will bring it out to the house. So it wasn't until this portion here, this last post office, that we really cared about the street and the house number, and that was for the delivery on the distant end. Well, that concept exists on TCP/IP networks as well. Same exact model, except for the portions that we're going to have, we're going to name a little bit differently. When I have a computer N1 that needs to deliver a packet to a computer N2, it's going to go through that network as well, this time a TCP/IP network. Once that packet is delivered to the first router, which is analogous to that first post office, what's going to happen is it is going to divide the IP address into two distinct parts, the network portion and the host portion. And when it does that, it's going to use just this network portion, as it did here, the city and the zip code, to get through the backbone of the network. And it won't use the host portion until that last leg, once it's at the distant end router and needs delivery to a specific device. The network and the host portions of an IP address are what is known as its natural parts. So what we've got to discuss now is, where does that division take place? And the answer is that it's different depending on each class of address, the A, the B, and the C, that have the ability to hand out individual addresses to host. All right, so this is what we're going to find. The rule for a Class A network is that the network mask, which means the portion of the IP address that is set aside for the network, is the first 8 bits. So let's talk about this again. Remember that we had 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And this continued up to the point that we had 32 bits that represented the IP address. And it's saying these first 8 bits here are dedicated for network. And what does that mean? That means that if I have a total of 32 bits, the first 8 are network, then I mean simple math is going to tell you here that 24 bits are allowed for my host address. And with the Class B, it changes. It says the first 16 bits are the network, which is these here. And obviously that leaves us with 16 for the host address. With the Class C, we're dealing with 24 bits that are dedicated to the network portion. So that's the first 3 octets are network, and that last 8 bits are the host. This is the default breakdown per class. In classful addressing, and that's what this is called, we cannot change that. It's pretty inflexible, and in fact, classless addressing, which we're going to talk about when we deal directly with subnetting, is what gives us more flexibility and greater range within our networks. But we have to cover class full first, and luckily enough, it's the easier of the two. So let's illustrate why we say this model is inefficient. What I have here on the side is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8 bits that I'm going to represent the different combinations available. So this is an octet. If I have all zeros for all the binary bits, I have a decimal equivalent of 0, right? And if I have all ones, that equals 255. This is what we discussed on the last whiteboard. Now, in between here, I have every combination in between. 1, 2, 3, all the way up to 254, then 255. What does this mean to me? That means I have 256 possible decimal values identified here, right? But there's a rule. There's always rules within subnetting. And the rule is that 0 and 255 are invalid host address. In fact, they're invalid network addresses as well. So as a general rule, you can't use these. So you can wipe this one off, and you can wipe this one off as usable. And when you do that, you come up with 254 usable host address or usable network addresses if you're just dealing with 8 bits. So in this case, we're dealing with 8 bits. That means that these hosts, or these network addresses that are available, there are 254 possible networks. But now the big number. What does that mean as far as the host? How many hosts do I have available then on each one of these networks? And the answer to that is 16,777,214. So this is where we talk about this system being inefficient. That is a lot of hosts, and most networks or most corporations aren't going to use that many hosts on one network. All right, so let's move into the class B now. What we're going to have here is 16 bits that we're dealing with as far as the network address. And the result of that is 65,534 possible networks. Now keep in mind, this address scheme is set to deploy on a global basis. So you want a lot of possible networks to be handed out, because the growth of the internet was unknown when they first came up with IP, and they said, you know what, we want to be safe. Let's add some room to scale up. And so they have 254 networks here, 65,000 plus networks here, and down here, as far as networks, they have 16 million plus possible networks that they could hand out to different corporations. And that means, though, again, on the wasteful side, when I had each of these networks here in a Class B network scheme, each one had the possibility of hosting 65,534 hosts. Again, a large number for one network. All right, because you've got to keep in mind that networks in a classful environment, you have a router here, and a network will hang off of one interface. There's almost never an instance that you're going to have 65,000 hosts hanging out on that one local area network, right? So that's why it's inflexible. All right, and then we're going to finish up the model here with our Class C. The networks were 16 million plus. The host, much more manageable. We're talking about 254 per network, which really is what we normally would have as a max on our local area network. Let's get to a clean whiteboard so I can show you the results of everything we've just discussed. And that is that we are going to have a mask, a default mask associated with each of the addresses. Here we have Class A address, Class B, and Class C. What we're terming the mask is exactly what we just drew out from that information. It is the division between the network and the host portions. You see it here in a Class A address, here in a Class B, and here in a Class C. And you can see that with the denoting of an N for the network portion and the H for the host portion. Now the rule is in the default mask that anytime you have a network portion, you're going to represent that with ones. Anytime you have a host portion, you're going to represent it with zeros. And that's why you see 8 ones, 24 zeros in a Class A, 16 ones, 16 zeros in a Class B, 24 ones, and 8 zeros in a Class C. Now that I know the default mask associated with each of these classes, how do I apply that to an actual IP address to come up with the network and the host portion? We're going to find that here. The tool we use is called the logical AND tool. The logical AND is a Boolean algebraic function, and its purpose is to apply the mask that we have down here to the IP address and come up with the division between the network portion and the host portion in that IP address. As we talked about earlier, we need both of these portions to address our hierarchical need so that we can get packets across our network. All right, well, what I have here is a representation of an IP address, and the IP address is 172.16.1.2. It's the one we broke out earlier. And I have a default mask of a Class B network. So why a Class B? Well, 172 is between the numbers of 128 and 191, which automatically makes it a Class B, and that default mask we'll find here with 16 bits for the network. The logical AND is actually a very simple process or tool to use, and it's as easy as taking a picture. Once you line everything up within your frame, all you have to do is push the button. In this case, pushing the button is applying a rule. All right, so what we have to do is line up in line our 32-bit IP address and our 32-bit default mask. Once we've done that, we apply this simple rule. The rule in logical ANDs is if I have a 1 on the top line and a 1 on the bottom line, the result of that is going to be a 1 down here. So you see that. And the easiest way to remember this is pretend like this is like you're multiplying these two lines. 1 times 1 is going to equal 1. 1 times 0 equals 0. 0 times 0 equals 0. And 0 times 1 is going to equal 0. So if you remember that, you simply apply that here. A 0 times 1, that's going to be 0. 1 and 1 is 1. 0, 1, 1, 0, 0, dot, 0, 0, 0, 1, 0, 0, 0, 0, and then from there on, we have all zeros down here in the default mask. Because anything combined with a 0 results in a 0, we don't have to worry about what's up here. It's simply going to be all zeros from that point on. And what the result of that is going to be 172.16.0.0, because we see that here. This is the decimal equivalent of 172, the decimal equivalent of 16, and 0 and 0. This is our network portion of this original IP address. As I stated earlier, this is classful addressing, and what makes classful addressing so easy is that these default masks always fall in line with a bit boundary. That means that they are going to be, the separation will be at one of these dots. Remember, the Class A was here, Class B here, and Class C. So what that means to us is, once we know the network address of 172.16.0.0, all we have to do is zeroize the network parts and then come straight down with our last two octets, in this case, .1, .2, and now we have the host address that we need for routing our packet through the network. We have a network and a host. Let's apply that back to our envelope that we used in our analogy with the U.S. Postal Service. And what we're going to find is that we now have two distinct parts. We have our network portion, equivalent to our city and zip, and we also have our host portion. So that means now that my computer, N1, can deliver that packet to its default gateway that we talked about in the IP addressing video. Now it's in the backbone of the network. Once it's there, these routers are simply going to use the network portion only to route through the backbone until they get to the router that has knowledge of the 172.16 network. And by knowledge of, we mean that it exists out of one of its interfaces. Once we're there, that router has to find out and make the last leg of the delivery over to the host address, 0.0.1.2, and that takes place right here. So we have the source address here. What we really need for our delivery is the destination address also. I have an IP address here, 172.20, and we know it's .20 because remember our placeholders. 1, 2, the 4 is on, 8, and 16. So the 4 and the 16 place are on. Combine the two and we have 20. So 172.20.1.2. We need to do exactly what we did before. Apply our default mask. It's still a Class B address. And when we do that, we're going to come up with a network address of 172.20. Remember, it falls right through because all of these are ones. .0.0, and we're going to have a host address of 0.0.1.2. All right, so let me write those in. Notice that the host address on the source and the destination are exactly the same. This doesn't cause a problem. Remember our discussion that we went through that says that 123 Main Street can exist in town X and 123 Main Street can exist in city Y, and mail can still be delivered from one to the other because of this, the combination of the two makes a different address completely. Same idea here. All right, so now we have the 172.20 network that exists here, and we were able to route to it, and the last leg was to host 0.0.1.2. In this nugget, we started by looking at the decimal to binary conversion technique and understood that the place values in binary starting at the right were 1, 2, 4, 8, 16, and kept doubling onward. And that was the key to understanding the conversion between binary and decimal. We also looked at the IP classes. We finished up this discussion by showing the logic behind the default ranges for each class. Then we illustrated the need for an IP address to be broken up into a network and a host portion and how that fits into the hierarchical addressing scheme used in IP. We followed this with a look at the default mask for each of the IP address classes and saw how it is used to divide the host and the network portion. We called these portions its natural part. And we ended up with a look at the tool that brings us all together, the logical AND. It's used to apply the default mask to an IP address so that we can come up with the divisions of network and host. I hope this has been informative for you, and I'd like to thank you for viewing.